Hi there. Today we are going to look at collisions. Last class we looked at explosions, cannon and a ball coming apart, exploding away from each other. One goes to the left, one goes to the right, conserving momentum. Now we'll look at collisions. A car is parked, another one comes and hits it, or both cars are moving towards each other or in the same direction. What happens? Now, the different types of collisions that we would be looking at are elastic collisions, and these are collisions where both momentum and kinetic energy are conserved. So primarily we said that momentum before was going to equal to momentum after. In an elastic collision, which is usually happens perfectly with subatomic particles, however, they can be well simulated in a lab using magnets during the collision so the objects don't quite collide with each other. The reason they lose kinetic energy when they do is because of deformation and sound and heat and other energies that are created, which can't come from anywhere. They've got it, when energy must be conserved as well. So in this case we see that in an elastic collision, the kinetic energy before the collision would equal to the kinetic energy after. And we could certainly write that as Ke initial equals Ke final. And it turns out that if there are two vehicles, then we would have something like 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 prime squared, which would be the velocity after, plus 1/2 m2 v2 prime squared. Now we'll look at elastic collisions in a different lesson. Today we will be mainly concerned with inelastic collisions and perfectly inelastic collisions. We will start with this one first. Now in an inelastic collision, some kinetic energy is conserved, but some amount is lost. However, momentum is always conserved. I want you to be sure that you understand that in all three collisions, momentum is always conserved. It's just in this one here that only kinetic energy and momentum both are conserved. Okay, in this case, only momentum, MC, momentum conserved, momentum conserved, momentum conserved, and here Ke conserved. Okay, so today we will look at perfectly inelastic collisions, and next lesson we'll look at inelastic collisions. In a perfectly inelastic collisions, the maximum amount of energy, kinetic energy, is lost. And in a perfectly inelastic collision, that happens when the two objects colliding stick together and move off as one object. Okay, so that's going to be primarily the type we're going to look at today. Is a perfectly inelastic collision. That means the two objects, maybe one is moving this way and one is at rest, and once they collide with each other, they are both moving off, stuck together in the other direction. Alright, so let's take a look at a few examples. The way we would set up these equations, we again start with our same premise that initial momentum must equal to the final momentum. We could break that up further. Pi is the initial momentum of the two objects, and then this would be the final momentum of the two objects. Clearly you must understand that neither one of these individually are conserved, but the sum of this is conserved. So if this answer turns out to be 5, then this will also equal to 5, the sum of all of this versus the sum of all of that. Now, because they are going to stick together, their final mass will become the sum of the two masses. So we could really rewrite for perfectly inelastic collisions, okay, this is for perfectly inelastic collisions, that we can rewrite the equation this way. So that here is your Pi, your initial For both of them, they are not stuck together here. And then this is, because they're stuck together, this is the final. All right. A lot of cases, they might call something an inelastic collision, but it's actually a perfectly inelastic collision. You need to read the question and see if the two cars stick together, then we have a perfectly inelastic collision, and then this is the formalism or the equation we should use for that. Well, let's go ahead and take a look at a couple of these and see how we would employ them. So we have a boy running onto the sled, and if you've done this on a skateboard or on a sled, you know that once you jump on it, the sled and you are both going to be moving in the direction which you were running. So again, we use the same thing. We'd say, okay, m1 v1 plus m2 v2 is going to equal to m1 plus m2 v final. And generally, we are looking for this guy here. Like, what will be the velocity of the child and sled immediately after the child jumps on the sled? It's a 40 kg boy running at 7 meters per second onto a 10 kg sled. So let's call the boy 1 and the sled 2. And in this case, we have 40 times 7. It's very important that you put m1 with v1 and not mix them too. So maybe you want to write these here, v1, and then this would be m2. And so that plus, the sled was initially at rest, so m2, which is 10 kg, would be multiplied by 0. We can essentially ignore that. And now we add the sum of the two masses together, the 40 plus the 10 times Vf. We put that together, that's 280 plus 0 is equal to 50 Vf. So then dividing both sides by 50, I get Vf is equal to 280 divided by 50, which turns out to be 5.6 meters per second. So he was running at 7. Now he's added some more mass onto his system, so he is going to slow down. This would be the new speed with which the boy and the sled are going to take off. Okay, hope that makes sense. We'll look at one more example. And again, you could stop here, stop the video, try to work this on your own, and then see how it works out as we proceed with the video. All right, so a very similar situation. I'll call it A and B this time. So I have MA, VA plus MB, VB. That's the initial momentum of the cars here, is equal to M1 plus M2 times Vf. And that's what we're looking for. What's the final velocity of the two cars when they're stuck together? So again, we'd have 1,000 kg here times 5 plus 2,000 times 2 is going to equal to m1 plus m2. That's 1,000 plus 2,000 Vf. Gives me 5,000 plus 4,000 is equal to 3,000 Vf. So 9,000 equals 3,000 Vf. If I were to divide both sides by 3,000, then I get Vf is equal to 9,000 over 3,000, which is just 3 meters per second. So the sum of these two cars, the combined mass will move off at 3 meters per second after the collision. In this case, both cars are moving in the same direction, In the previous case, one of the cars or one of the objects was stationary, and now we'll look at one more case. And in this case, both blocks are moving towards each other, but our formalism or our math to do this would still be the same. I'll call this 1, call this 2. I'll go back to black ink, and so I have, I'm going to write it here, m1 v1 plus m2 v2 is equal to m1 plus m2 times vf. Okay, so back on, m1 is 4 and v1 is 4 because this mass is moving at 4 to the right, plus m2 is 1 moving to the left, which would be negative 6 meters per second. So this guy's moving here at negative 6 meters per second. This guy's going at 4 meters per second. And that's going to equal to m1 plus m2, which is 4 plus 1 times vf. So that's 16 plus a negative 6 is equal to 5 vf. That would be 10 is equal to 5 vf, or vf is equal to 2 meters per second. Now, it's important to note that the original momentum, the total momentum, was 10 for both these guys. So the final momentum is also 10 for both these guys. And so then we go ahead and divided both sides by 5 here to get Vf is going to equal to 2 meters per second. Because this number is positive, we know that these two masses, when they're stuck together, will be moving towards the right because we got a positive velocity. It's kind of cool that we can determine what the final velocity of these two masses are going to be once they have collided with each other. So again, we've been looking at perfectly inelastic collisions, and I'm going to show you one more with a little slight different twist to it. We have a blue freight car. This has the mass of 10 tons and it's rolling at 108 kilometers per hour along a level track. It collides with this brown freight car, which is at rest. If the speed of the both cars, what is the speed of the both cars, if the speed of the both cars together is 36 kilometers per hour, what was the mass of the brown car? Okay, so that's what we need to look at. So I'm going to call this guy 1 and this guy 2, because if I use blue and brown, it'll be the B's in both cases, and that doesn't really help. Okay, so call this 1, call this 2. So our original equation again is m1 v1 plus m2 v2 is equal to m1 plus m2 times vf. Now we don't know the mass of this brown car. That's what we're looking for. We're looking for m2. Now over here we have m1 is 10, and I'm not going to convert this to miles per hour because or to meters per second, because I can see that these will cancel out anyway, so I don't need to do that. The velocity here would be 108 plus m2, which is, I don't know m2, but I know the velocity is 0, so that's because it was at rest, right? And that is going to equal to m1, which is 10. So let's write 10 plus m2 vf, which is 36. So now I have 10 times 108, which should be 1080, plus 0 is equal to 10 plus m2 times 36. So then I have 1080 here is equal to, and I'll multiply this out, 360 plus 36 m2. Okay, all I did was distributed that in there. And I'm going to subtract 360 from both sides. So then I have 1080 minus 360 is 720. So 720 is equal to 36 M2. So then M2 would be 720 divided by 36, and that would be 20 tons. Okay, now because we are not looking for momentum itself, meaning we don't need to find anything in kgms, we don't need to go through these conversions here. Now, had the question asked for not the mass or not the final velocity, but what is the total momentum of the system before or after, or any part during the process, if they ask for the momentum of a certain car or of the system, then we really don't have a choice but to convert this to meters per second and this to kg. Because remember, in our SI system, everything is either kg, meters, or seconds. And so anytime we need to find any of these quantities, such as newtons or momentum in kgms, we would need to convert these to the metric system. Okay, I hope that helps. Next lesson we look at the inelastic collisions, and then we'll further on look at the elastic collisions, which is normally not a part for the regular high school level kids, but the honors and the on-ramps or AP students would certainly need to know about that. So we will cover that in one of the videos later as well. We'll see you later. Bye for now.
Thank you for watching. If you liked the video or found it helpful, please like us.